Welcome to our presentation. My name is Bats Barami. Together with Nick Morzin, we are going to talk about recent development in our quantum framework. One thing that I should mention is that, in fact, there are two other talks today immediately after our talk. There will be the main big developments that are happening, in the past year since the last tech conference with regard to quantum functionalities. Make sure that you don't miss those talks by the other developers who are working on quantum framework. So me and Nick, today we are going to focus on two major development that can be very useful in many different fields of research, especially for those people who are working on quantum information science and open quantum system, quantum thermodynamic. Of course, the big news and the hype is still about quantum computing. There are lots of functionalities related to that, but today we would like to focus a bit more on more conventional calculations that we do in quantum information science. So as usual, installing the packlet, you see long list of functionalities that we have. The way that I want you guys to think about it is mostly think in terms of fundamental objects. Okay, for us, one fundamental object is the way that we define our basis, the basis of our space. Then we have another object for the state, and then there are a collection of functions. See them as transformation of your state, and that transformation can be done in a many different way. It can be done as an quantum operator. It can be done as Hamiltonian evolution. It can be done as a quantum channel. So the way that to do that, it could be very different. So and we just realized as always, when you do live coding, there are potential
Weird.
errors.
This is weird.
I think it happens
Okay.
we
Ignore
will,
it. Just ignore it.
yeah. Anyhow, let us start with with one of our beast functions, which is quantum evolve. So the idea here is that whatever that determines the evolution of your system, feed it into quantum evolve, and you will get your final state at any other time. So in quantum, usually there is an operator. We call it Hamiltonian. So here we are considering a fancy Hamiltonian that is kind of you have a bunch of spins, two particles, and there is some interaction. So call it a spin chain with the particular interaction. Okay, so that's the simplest way of thinking about that. And then this is not an isolated system, because if it was an isolated system, that Hamiltonian would determine the evolution. Environment is doing something with that system, and of course that's the biggest challenge that we have for quantum computing, how we can eliminate the effect of the noise. But anyhow, one way of including noise is through some jump operators. These are basically the typical Lindblad jump operators, and then just set the parameters. By the way, later on we are going to show it can be done in a many different way, but this here, let's do it in a numeric way. Everything, if there's a symbolic solution, it can be done in a symbolic way. So what you're going to do, you're going to feed everything into your Hamiltonian, and then at any given time, so you can ask what's happening, and now we are
I
seeing
think I
some.
have some. I know. Sorry. I polluted my session somehow. All right.
And I see the one thing you see whenever you are using Wolfram Quantum Framework, that summary box that you see, it contains some interesting information. For example, it tells you it's a parametric state, meaning you can feed some parameters. You see here, Nick is feeding parameter 0.4 as the value of that parameter. Later on, we will discuss about parametric quantum objects toward the end. But it's Wolfram mathematical, a very strong visualization functionalities. What you see here is the amplitude. So the bar represents the absolute value of amplitude, and the color represents phase. Okay, so this is one way of visualizing the amplitude of a quantum state. And for the sake of presentation, Nick changed time, I don't know, put 0.5, whatever. Let's do that another time.
Maybe not.
Yeah, you see, that's how it evolves. And of course, you can do a lot. So in this example, we have a spin chain, and then you can ask, what is the expectation value of some observable at each location in that big spin chain, and then you can do lots of visualizations. historically, people, they love visualization in the block sphere. So this is like, the case that you see that zeta is basically the specification of our environment. That environment can do many different things. Like, one thing, like, we call it like an environment that acts as like, anti-correlation between, particles, or, a correlation between the particles. But anyhow, long story short, you have absolute freedom in doing, whatever you want. And each of your, like, spins, it does a dance in the block sphere because the environment is interacting with that. It goes inside that sphere. In quantum, we would say, your states become mixed, and then, like, you get a, final state. So that's basically like, a simple visualization of your spin chain. It's very nice because, like, just imagine, like, if you have a spin chain, what you can do for all of your spins, you can see, like, this dance, how the dance inside the block sphere is happening. Uh, of course, this is not the only visualization. Like, the second half of, like, this talk, we are going to talk about, like, the other way of thinking about, like, quantum state. And then you can, like, ask for some observable quantities, like, what's going to be, like, if you measure Pauli X, Pauli Y, Pauli Z, like, which is basically like a spin, along different directions, what's going to be the expectation value? And that's how it evolves in time, depending on, like, how we set the environment. You notice here, like, even you have the freedom of, like, specifying how environment behaves. Now, talking about expectation values, it's, remember, like, it's computational. Okay, like, those typically those formulas that we have in our textbook, they are very inefficient to do computation, and that's why, like, you need smarter way of, like, going after expectation values. And this is the way that, like, this is our plan here, that kind of, like, selling you guys the idea of quantum in phase space. So basically, instead of, thinking in terms of that block sphere and everything happening like that, let's change the basis, and let's look at, like, quantum state in a different basis that resembles, like, more classical probability theory. Side note, our quantum framework supports any dimension. So that's why, like, just to show you, like, this generalization, we are going to a higher dimension, which is dimension, like, 3, and the number of, like, qubits. Now I have to remember, how do we call, like, a qubit with dimension 3, Nick?
I would say qubit.
Qubit. Okay, so that's the common name that people use in the literature. So there are 3 of them. Okay, so there are 3 of them, and then, like, each of them, like, they are in a three-dimensional space.
It's really one qubit, but we do have 3 Lindblad.
3 Lindblad. Okay. The environment or the surroundings, it's coupled with your system in 3 different ways. Like, that's one way of seeing that. And of course, like, we are setting everything here random just to show you a generalization. The evolution, like, this is really, I think, the personal preference of, like, scientists. Some people, they like, the Hamiltonian approach. Some people like, from classical mechanic, Liouvillean approach. But anyhow, we support both of them. I think, like, the connection between the two is, like, in one case, like, you don't see that imaginary one, it is inside your super operators. In the other case, like, it is separated. Nick, is there any other fundamental difference between the two?
No, they're literally just different by one imaginary unit. It's just in some situation one is more convenient to use than another.
For example, those of you, like, you are familiar, like, you can do quantum computation in many different, pictures. Like, in some pictures, Liouvillean approach is more convenient because, like, setting that up, like, it's much easier. But if you are working on Schrödinger picture, like, typically we always use Hamiltonian. Now let's look at, like, many different ways that you can do this sort of, computation and obtain your expectation values.
Well, first of all, just different ways of evolving your quantum state, right? When you just evolve by constructing this Hamiltonian that consists of an actual Hamiltonian, right? It's just the more generalized Hamiltonian. This consists of the usual Hamiltonian plus Lindblad operators and some gamma factors, right? Damping rates, what they call it. So you can use the most simple way of evolving it, actually maybe more direct one. Direct way of evolving it would be to actually just feed this Hamiltonian, those Lindblad terms and gamma terms, your initial state, and some your symbolic parameter, which is not even need it by default, right? It's gonna generate a parametric state with some formal parameter time, and that's your final state. And you can then query it like, okay, what happens to this state after 1 unit of time passes, right? But you can do it like in many ways. Because we have this convenient way of generalizing operators, you can just bunch all of these terms together in a single super operator. That's what we call like this generalized Hamiltonian. It's like mixed map or super operator map. Sometimes call it. I will explain what it means later, maybe there's time. And you can like just evolve it like that instead. And the result is essentially the same. If you like do some like the traditional form of this final state, if you do it, I'm supposed to compare it to this one, right? So the results are the same. And there are many ways of doing it. You can instead of evolving the initial state, you can evolve the operator itself. Again, ask what would be that operator after the 1 unit of time, and then act with it on the initial state, and you'll get the same result, right? You can do it numerically, like this is by default doing some symbolic computation, so it's a little bit slow, and then it substitutes 1 for time. But you can directly evolve using some numerical integration. It's a little bit faster, right? By using this, again, generalized Hamiltonian. And there's many ways of doing it because our Hamiltonian is not time dependent. You just literally can just exponentiate it, right? And then apply it, because this is just produces another operator, and then you apply it to state, and that's how you can get. Because here's like for what time you want to evolve it, and that's what the difference between those Hamiltonian and Euclidean is.
We call all of them like we wrap it like as a quantum operator, but like in many textbooks, like these animals, like these are what people call as super operators. These are the operators, like part of that it acts from the left, from the right, like but you can have a unified. Remember, like the core idea of like Wolfram language is like you have some super functionalities, and those super functions, they can eat any animal. So like these are like these quantum operator is one of those cases. It can you can have many different strange transformation, but by definition it is still a quantum operator.
Yeah, that's basically what we're trying to generalize. We have just quantum objects, and we just try to invent some nice hierarchical levels of like abstraction, so that our operators are as most general as possible.
Yeah, and this is basically like
we still have ideas how to improve it.
Like since Nick is also involved like with Quantum Institute and Wolfram Physics Project, remember like this is philosophical idea of like Stephen himself, like reduce everything into the most abstract operations, like what are the most minimal objects that you can have, and then out of those very minimal objects, like you can get a very complicated like behavior. And this is like what we do. I'm gonna brag a bit here, like I can safely claim we are the only quantum framework out there that can covers all these strange features. Like anybody who knows any other quantum framework, try implementing super operators there. Like you will see how complicated it is. But anyhow, we have a lot to cover. Let's move on slowly to the phases space.
You're right. We have arbitrary dimension. We have arbitrary types of states and operators. We can do type like symbolic stuff and all of that. But here's like another way of doing, for example, of computing expectation values. Right? You can again generate some random observable, which is just another operator, which has to be Hermitian usually, but it's not a constraint, just a physical constraint, not the numerical constraint. You can evolve the state, right? This is just the final state, or we could have used initial one, and you just use the construct a measurement operator out of that observable. You have to diagonalize it. Maybe it's not necessary, but I think it's not necessary. Let me check. But it actually produces the same result. Because I believe, yeah. So it produces a measurement object, and then you can ask, yeah, I think it's the same. Right, so it's not necessary. So that's most direct way of actually computing the expectation value. Just make an observable measurement operator, act it on a state, and ask for mean. But you can do some kind of Heisenberg picture evolution instead of making measurement of the final state. Of the evolved final state, you can actually evolve the observable itself. That's how you have to transform it into a state, evolve it backwards. That's why there is minus sign there.
Mhm.
Right? Ask what the observable is after 1 unit of time, turn it into operator. It's a bit tricky, but that basically shows you that there's many ways of doing the same kind of thing if you know your theory well. I think
Yeah,
this
the top
diagram
one is
gives me.
basically showing a picture. The lower one is a Heisenberg picture. Like, it's just in one case, we evolve quantum state. In the other case, you evolve your observable. And by the way,
Yeah.
like, this way of calculating mean value is practically the closest to the experiment. So in a real experiment, like, you do those measurements and you get the mean values.
Yeah. This is like the most direct way of doing it, because this is like just results into some quantum measurement operator which knows about all your eigenvalues and their probabilities, and then you can just average them out. That's how you compute it.
Mhm.
Yeah. But like transition into more advanced topics is like we can do exactly the same kind of way things in phase space. It's just like some sneak peek. What you can do is like you can do the same kind of evolutions after transforming your states in the phase space picture. You can transform your Hamiltonians in phase space picture. You evolve it and essentially get the same results, right? You can exponentiate before or after. You can like mix all of this objects
Mhm.
together. So that's how you can play with those objects and learn about the theory. And the observable is the same thing, right?
Mhm.
So, but in more detail, I want to quickly tell you about what is this phase space is all about. It all revolves around this concept we call double space. It's like a pre-phase space, but it's more direct way of introducing it from the Hilbert space, which is the most known space in the quantum theory and quantum computation. And just to show what it is, essentially is if you have a random state like a qubit, right? It can be mixed, the doubling of that state essentially introduces an extra qubit. But what it means is essentially what you did is just took a density matrix and flattened it, right? So you can see that the amplitudes of that double state is just the elements of the density matrix. So it's not very special operation, right? But you just essentially turned one qubit into two qubits, but now your amplitudes are just the elements of your density matrix. Sometimes this operation is also called vectorization,
Yeah.
right? But in the diagrammatic way of doing the same kind of thing, you can also think of this doubling procedure as just taking your state and just putting it besides its conjugate version, right? So we have this state, now we have two states. But that's only when your initial state is pure, so you can actually represent it like this. It's actually more helpful when your states are mixed. Then the same kind of thing is actually when you double it, you again do the same thing with the density matrix, but now we don't have to like put it side by side. You just have the new object, which is I believe would just be like this. In the circuit by default, we show our density matrices by this bold border to distinguish them. But when you essentially perform this double operation, well, it's not gonna show you, I guess. I think you should append. Yeah. Essentially, instead of just putting it side by its conjugate, you have to this flattening actually ties them together, because now your density matrix is a bit mixed together. That's why we call it mixed. So you can't really separate them. So that's why there's some dashed line between those things. But
And I
yeah,
guess,
but
like,
you can do
here,
the
like,
same kind of operation in not just with states, but also operators. But for operators, is a little bit more involved, because for operators we want to preserve the ordering, so the wires of the operators, because we assume that operators live on the wires, so they act as gates in our circuits. So essentially, when you double the operator, what we usually mean by that is you again, similar to a state, put it besides its copy, its conjugate copy, and then you also carry and then carry its wires, so that it still has a single wire as an input and as an output. but it's now doubled. It has higher dimensions, right? So if you actually show the dimensions when you double the whole circuit, right, you can show that, by the way, that this is the same thing as doubling the operator, this operation of carrying and carrying this operator with its copy. But you can just double the whole circuit. And now your wires are just have higher dimension. And you can work with these objects too. So you can contract them, copy the underlying state, and you work with this in this double space now. And now you can, essentially, that's what allows you to work with all kind of mixed operators, mixed states, channels, and measurements more naturally, because everything is vectorized and looks like a vector instead of some weird matrices that has to be transformed by the joint operations and all like that. You don't have to worry about that, because now they're just vectors and you just compose them with dot product as usual.
And another motivation is that, like, now, like, if for example, in the circuit above, you see all of those wires, like, the dimension is 2. So basically, the information that they are carrying inside that those amplitudes, they are complex number. When you do the, like, the doubling, like, in that machinery, like, now everything is real number. Okay, like, so, like, that's one way of, like, so it's a big step closer to the classical picture that you can have from those, like, quantum objects. And I think, like, the diagram on the top, like, it kind of justify our motivation to call it doubling rather than, like, vectorization, because, like, maybe vectorization makes sense for states, but not for any quantum object. Here, like, it's literally, like, you double them, and then, like, because it's just kind of copy of each other, so overlay them, and then you have, like, higher dimensional wires.
Right. So yeah, and those objects allow you to work more conveniently with measurement channels, because doubling this, well, essentially this is like our special types of operators that already represent this vectorized form of measurements, because the way you can represent them by just this special mixed maps, right? And you can just work with them as the usual operators, and you don't
If I may add, like,
you don't even have to double the dimension and all that. And it's like the same dimension. It's like it still acts on a qubit, but because it's mixed and underneath it holds this density matrix instead of just the vector, it can it understands that it has to act in a joint fashion and transform the state in a correct manner.
and of course, like, for any of, like, this generalization, like, a very important question, and everybody should ask is, so what? Okay, so why bother? Somebody can say, okay, why bother? Like, why I need those generic, like, definition of measurements? Very simple reason is that there are many different paradigms for quantum computing. One of them, measurement-based quantum computing, and this is the object that you need when you want to do, like, measurement-based quantum computing. Okay, like, we have, like, community posts about them, and you can look it up. But, like, if you want to implement it with the conventional definition of measurements that you had, it's not just not doable. With this generic, description, you can have, like, support for measurement-based quantum computing.
Yeah, that's fine. Maybe, well, maybe I can show the picture, what we mean by that really quick.
Think about, like, measurement-based quantum computing. Yeah,
yes.
this thing.
Yeah. So this is the special mixed measurement that you can just integrate into a quantum circuit and it still works, because it still can unroll itself into vectorized form underneath and contract correctly, because we allow for such a thing. You can even make controlled measurements like that, because you can treat them as operators.
So basically, like, a quick comment here. You see, like, the first two part is, like, your preparation in measurements quantum computing. What you do is that you prepare a very big system which is completely delocalized, but it has a very high entanglement. The rest of the operation is only measurement, and this is, like, one interesting feature about, like, this paradigm of quantum computing, because you don't have the headache of, like, those gates and then, like, removing the noise, etc., etc. It's just you prepare a very entangled quantum state. The rest is conditional measurement, and based on the measurement, you decide what to do next. And it resembles exactly what you have in the typical gate-based quantum computing. Of course, like, it's also very interesting, like, those generalization for foundation of quantum theory. That's why, like, as we were developing these functionalities, we realized, like, okay, now we need a sort of super operator that covers all the phase space. And this is like, our quantum phase space transform.
Yeah. So that's what we basically what we showed now just was the double space, which is like an intermediate phase space. But if you generalize this concept, essentially what is double? After you double your state into this double space, you can then think about how you can change the basis after that. So you can introduce some special bases. We have many bases like for the Hilbert space, but also for the double space, and that's where those bases we usually call phase space bases, right? So that's the basis that is like the second argument for this new function phase space transform that allows you to transform all kind of quantum objects into this phase space representation, right? So for example, if you transform to some Feynman state, Feynman basis, this is like a phase space where all the amplitudes can be, well, it's essentially they do act as quasi probabilities and things like that, right? You can transform into another state, which is essentially the same thing, I think. There's a like more common one, Wigner, also cubism. This is like the actual probability representation. Those are not just quasi. This maybe has a bad luck. Let's try sigma. Yeah, so this state has an actual negative probability. So those amplitudes in phase space are can be treated as negative quasi probabilities. But in this phase space basis, it is always just probabilities. So we can purely treat any state and even any operation, any quantum process in this particular basis or some other similar information complete basis as purely as probability distributions. And we can just show you can transform measurement operators, unitaries, operators, even channels, right? But it's like you can even make your own basis. For example, you can transform outputs as the usual phase space basis, but inputs as its inverse. And this basis actually allows you to transform any unitary, any channel, any quantum process into just purely probability distribution. So you will always have positive amplitudes that sum up to one. So any quantum process in this particular basis would look like a probability distribution, which is very nice for the research, and that's what we're doing currently, exploring these ideas of probability representation of quantum objects. And essentially, when you do this, of course, it's not in the same basis. You still have to make an inverse. So essentially, in the same inverse basis, you have to think about how the identity looks that transforms from this direct basis to the inverse basis to the direct basis, like inversing the direction of your wire. And that's the only non-classical matrix, essentially, that you have to explain, at least for qubits, that has this any quantum component, because every other quantum process in this basis would be a probabilistic one. So, and that's essentially like what allows you to offload every quantumness from your quantum circuits just into the single identity operator, or essentially into the wires of any circuit. So you can take your arbitrary circuit like this Fourier transformation, turn it into this basis. Now every object here, like every operator, every gate is now just a conditional probability table like that, transforming classically your probability distributions, but every quantumness is offloaded into the wire, which looks like exactly like this matrix and nothing else. So, and I guess, and that's just to prove it to you that every operator in this circuit is just some things with positive numbers, no negativity, no complex numbers in there. This is an actual representation of those objects in there, and you can work with those objects instead.
By the way, like, we only have a few seconds here, Nick.
Yeah.
But I think, like, we can go over time a bit, like, one thing, like, that Nick mentioned. I want to rephrase it one more time. Like, remember that, like, from foundational point, like, there are a couple of motivations for this form of, like, computation. Like, one motivation is just like, an alternative way of doing computation, because many of the textbook computation, they are badly inefficient the moment that you increase the size of your system. It's like after a couple of a few qubits, there is no classical computer that can simulate your quantum system. So that you have that's one big headache that many people have. Another big motivation is quantum foundation, the whole story of how you can reduce machinery of quantum theory into something much more minimal. As I said, this is the story of Stephen Wolfram himself, and everything that we do at Wolfram Research. We always love to reduce things into something much more minimal. And our understanding currently is what just Nick told you. At each of those gates, everything that is happening can be represented as a pure classical probability theory. But there is a step that that where that quantumness comes, it's from one to the next, there is some sort of transformation, which yet we have to explore that more to understand it better, that introduce some sort of negativeness into your machinery. Or maybe there are other interpretation, I know Nick has been thinking about could be different direction in time, or it could be a retro inference, or we are still exploring what are the consequences. There are more I don't I'm not sure if we have time to cover parametric circuits and ZX calculus that we have full support in our framework. If I may, there is an interesting question. What is the primary reference in which framework's notation is based on? Part of the notation is basically the conventional one that we have in the literature. Okay, it's which is Dirac notation. But keep that in mind, Dirac notation, it can be generalized. Okay, so it's this is Dirac notation, but in the most generic way. Like the example you see here, this is Dirac notation. It's useful, it's I know many of our users, they ask us about that notation for tiny objects, I don't know, 2 by 2, 4 by 4, for a small object, it's interesting. But the moment that you want to solve any real world problem, a problem that is interesting, Dirac notation is not that much useful no more. It's when it's a small, yes, but the moment that you increase this, remember the size increases exponentially here. That convenience, you're gonna lose it very fast. And that's the main reason that when you work with our framework, we don't show you Dirac notation. The first thing that we show you is that summary box that contains much more information.
Yep.
So let's see. Any other question? We have parametric circuits that are very useful, people who are working on variational method, etc. That's useful. But
right.
there are two other talks.
Those will be explored in next presentation.
Yes. I highly recommend. There are two other talks, on second quantization and also optimization techniques using quantum, so which are happening. I believe one of them right now. So if I may, let's wrap up here. Thanks for the time, everyone. Thanks, Nick. Until next time.
Thanks, everyone, for listening.
Thank you.